afternoon. This is the second lecture on properties of a pure substance. What we'll do today is revise what we learned yesterday, and then we will carry on to see different types of property charts that are there, how we can show states, and what are some of the common processes that can be shown on those charts. After that, we'll go to the idea as to what happens when the temperatures or the degree of superheat increases a lot, and that takes us into this discussion on ideal gas. So we'll reach that point where we'll begin the discussion on ideal gas today. Okay, so to revise, what we learned yesterday was that a substance can exist in what broadly we call two categories, what may be called not a gas or a non-gas, and a gas. And within gas, we have the most idealized situation, which we call the ideal gas, and then a real gas that deviates from this thing. This is the easiest thing to work with in thermodynamics, for the equation of state is very simple, and that is the central idea of all this discussion on properties of a substance as to how can I get all the properties for a given state if I have one, two, or if I have minimum two independent properties are specified. Then we went through a discussion about how a material behaves, and we took the example of water at ambient conditions and looked at what happens to it when you do isobaric heating. And there we came across that substance can exist in many phases. We said that there is a compressed liquid, which can also be called as a subcooled liquid. Then we came across a saturated liquid, saturated vapor, and superheated vapor. And then something which is beyond this, we call it the supercritical fluid, or the dense fluid. So we learned that a substance can exist in so many states, beginning from ideal gas, which is one extreme, to real gas, superheated vapor, saturated liquid, compressed liquid, and if you go below temperatures below that, then you're going to have the solid phase. Then we came across something which said that this and this, the saturated liquid and saturated vapor, can coexist as a mixture, as a phase mixture in equilibrium. So any mass fraction of liquid and vapor, if it is corresponding to the saturated state, it will be there in equilibrium. Then we said that in saturated state, pressure has a one-to-one correspondence with temperature and vice versa, which implies that these two are not independent properties, but basically they are only one property. And to completely specify the state, we need some more information. That information can come either from data on S or H or V or U. But we introduced one more parameter that will complete this definition of the state, which we called X, the dryness fraction or the quality. And the way we defined X is that X is equal to the mixture volume divided by the total mass of the substance in that. What we mean by this, we can call it say V total upon M total meter cube per kg. We took one example yesterday and we said that look, I have a vessel, there is so much liquid sitting here, the upper space is filled with vapor. Then what is the dryness fraction? And for that we define the system boundary as this one. And this is the dryness fraction we are now defining for this. It's not necessary that this is the only way in which a liquid and a vapor in a saturated state can exist with one another. Another example is a tube which is being heated, like the evaporator of a refrigerator or evaporator of an air conditioner. And at the entry of this, we say we put saturated liquid. Dryness fraction is 0. And we ask that the liquid was completely occupying the space inside the tube. What happens to this liquid as it gets heated and it flows through the tube? So as some heat is added, it forms small vapor bubbles which are largely floating in saturated liquid. As more heat is given, these bubbles become bigger and they still the liquid around this. And even more heating takes place, these bubbles start to occupy a larger space in the tube, and the liquid is now in smaller amounts in a very irregular fashion. And then we could have a state where there is lots of vapor, small amounts of liquid as fine droplets, and finally only vapor. So physically this is what happens in the tube. But we can always pick up a state at that point and say what is the dryness fraction here or what is the dryness fraction here. So you could have dispersion of vapor bubbles inside a large liquid, or in the other extreme, fine droplets moving around in vapor. This is also what happens in steam turbines where it's operating in the wet state. And in between, it's very irregular behavior, and we cannot really write equations and solve out and say what is the answer. But qualitatively, we can say that if I take a element here, what is the dryness fraction? And we know that as this heating takes place, x goes from 0 to x equal to 1, and then if more heating takes place, the temperature rises, and it is then a superheated vapor. So these are different ways in which one can encounter this thing, which is a mixture of a liquid and a vapor in a saturated state. In all cases, the definition relates to the definition as per the system is concerned. This is the system here. This whole thing is the system over there. And this is what we write. And we can then write that this total volume is volume occupied by the liquid, the F, plus volume occupied by the gas, the vapor, divided by the total mass. The total mass is mass of the vapor, mass of the liquid, plus mass of the vapor. The volume itself we can write in terms of specific properties. This is mf into Vf, which is the specific volume of the vapor. So that is the volume occupied by the vapor. And similarly, the liquid, mass of the vapor multiplied by the specific volume of the vapor. This is the volume occupied by the liquid, this is G, vapor, divided by the total mass. And then we can break this up, that this is mass of the fluid, which is the liquid, divided by total mass, multiplied by specific volume of the liquid, plus mass of the vapor, divided by total mass of the mixture, multiplied by specific volume of the vapor. And here we define this property, that this ratio, mass of vapor divided by the total mass. This is our dryness fraction. Sorry, this is V. This is V. This is X. This is a specific volume of the mixture. That is what we are trying to calculate. So this is equal to, this becomes 1 minus X times Vf plus X Vg. So the specific volume of this mixture or this mixture or this mixture can be calculated by a relation where we know the dryness fraction, we know specific volumes of the two phases. So although this equation looks like we have three variables on the right side, we have X coming here and these two coming here. But since these correspond to a saturated state, they are basically only one variable, which means that either we know the pressure or we know the temperature, and then from the property tables we can go and pick up Vf and Vg. So we are basically looking at only one variable here and one variable over there. That's what we need. We need two things, and that's what we can get from here. We can recast this equation and write X is equal to, as a function of specific volume. And if we do that, we get the answer that X is equal to V minus Vg, Vf, upon Vg minus Vf. That's how we can calculate it. And what it tells is that if V is equal to Vf, that means the entire volume is occupied by the saturated liquid state, then X is equal to 0. And if V is equal to Vg, that means there is only saturated vapor, then X is equal to 1. And in all applications, X will take a value between these two, and all these are defined only if we have a saturated state. So if say that we have in a vessel or in any system, we only have a liquid. If it is saturated liquid, its dryness fraction is 0. But if it is subcooled liquid, then its dryness fraction is not defined. Okay, so subcooled liquid is not a saturated state, so X is not defined. And similarly, the other extreme, that if you have only vapor in this, if it is saturated vapor, then yes, X is equal to 1. But if this is superheated vapor, then X is not defined. Sometimes somebody will write X is equal to 1, even though it is a superheated state. That's wrong. And same thing, if subcooled liquid is there, one says, no, there is only liquid there. Since only liquid is there, so X is equal to 0. That's incorrect, because state is subcooled, and for that, dryness fraction is not defined. So you need to take care of this. What we had also mentioned is that we got this property relation for in terms of specific volume, but the same thing also applies for all the other properties. So if you want to know that for this mixture, what is the specific enthalpy of this mixture, then we can say that H is equal to 1 minus X times HF plus X times Hg. And we said, ask the question, what is the specific entropy of this system? Then S is equal to 1 minus X SF plus X SG. And the same thing we can use for U. U is equal to 1 minus X UF plus X UG. So how do we get values of UF and UG? We discussed that a little bit yesterday, and what we have is tables and then computer programs also to help us with that. To give an example from the tables, the table heading will be saturated state. And in this table, the first column could be either pressure, or in some cases, it could be the temperature. If the pressure is given, then after that follows a temperature column, which is the saturation temperature at this pressure, Tsat at this P. If the temperature is the first entry, then the second column will be Psat at that temperature. So we'll have an entry here, like this, or these two entries. And after that, you will find that there's an entry for VF, VG, then UF, UG, HF, HG, SF, and SG. So all one needs to do is pick up where the pressure or temperature is, and you get all the saturation state properties coming out of there. So that's how we use these tables. In between, if these are discrete values, one has to do interpolation. Alternately, you can use either software packages, or you can go online, and there are online things where you say, they ask input two independent properties. And when you input those two properties, and they will give options. You want to input pressure and temperature, or pressure and dryness fraction, or pressure and specific enthalpy. And you pick that option, put those two values, it will tell you all the other properties that we are talking of over here. So everything comes up. One can also write these equations and integrate it with a program that then people do it when you are doing complete analysis of thermodynamic systems. You want to frequently call properties and you need that, so you write a small subroutine and get it up. There is one more definition that comes in, and that has to do with the fact that we define a new term, VFG, as VG minus VF. That means the specific volume change during the phase change. And similarly, we can define UFG, HFG, and SFG. So I'll just write down one of these. This is HG minus HF. And this is called specific enthalpy of evaporation. And its value at 1 bar for water is what you have learned in school. You have 540 calories per gram, or the equivalent in joules per kilogram. So if you want to express the value of X, say V, we can write that VF plus X VFG. That's another way of writing the same equation. Or in the earlier equation that we wrote, where we defined dryness fraction in this way, this we can further write as V minus VF upon VFG. In many cases, the tables will give values of these also, but there are many cases where they may not give these values. And the reason would be that if you want that, we can just calculate it from the values of HF and HG. That's what is there. And in the tables, this property relation also is always true. H is equal to U plus PV, the property relation we have already seen. So in some cases, even U may not be given, only H would be given, because in many engineering applications, H is what is used very frequently. So you will find that there is no properties for U given. No need to panic. We know that H is given, P and V are given. From there we can calculate it. So let's now look at some property diagrams. We also saw yesterday something that we have plotted, that how does this whole thing depend on the pressure at which this behavior is seen, and we came across two different set of lines. We were making temperature on this axis and specific volume on this side, and we came out saying that there's a line which is like this, where each point represents x equal to 0. This is the saturated liquid line. And then we said that there is the other part of this line which goes there, where points on this, they represent dry saturated vapor. And we define one thing, which is this point here, as a point where the differentiation between vapor and liquid phase disappears, and all we are left with is one state. This is called the critical state. And all properties at the critical state for a given substance are unique. They are just listed out separately. And last time we looked at the fact that if we started with 1 bar, what happens, and we made a picture of something like this. Then as the pressure kept increasing, we said that this goes up, and we start seeing lines over there. And similarly, further increase in pressure, this side is there, and all the states fall over there. In the critical state, there is a point of inflection here, and then it continues. And at pressures greater than the critical pressure, we do not see any phase change. This is what is called the supercritical fluid. And all states in this region, where they are above the critical pressure and above the critical temperature, they are called supercritical states. So we looked at this TV diagram, and now let's look at the TV diagram for some other substances. Okay, so let's look at this picture first. I have plotted what I have explained by freehand over there. These are real numbers for a substance which is a refrigerant R134A. This is a common refrigerant which you now see in refrigerators and some air conditioners. On the y-axis is temperature in degrees Celsius. The x-axis is specific volume in meter cube per kg. These are real numbers. What you see is that this line here, going all the way up, this is the saturated liquid states. And they are all pretty much like a vertical line, telling us that the specific volume change with temperature is quite negligible. But when we go to the saturated vapor state, we see this line coming here. And you can see a very large change in the specific volume, something which was like 0.001 or 0.002 of that order has now become at least 100 times bigger. It's now 1 over here and goes up to 2. So the first thing to note is that in many of the cases, there's a very large change in specific volume that accompanies this phase change process. Water at ambient conditions, when it changes phase from liquid to vapor, its specific volume increases by almost 1,000 times. So there's a huge increase in volume that takes place. But when we plot this thing in a different scale, we just change the y-axis, the x-axis to a logarithmic scale. Now you begin to see a curve which looks something like what I have been drawing. So on this side, this is the critical point at the top. The parameters are the same, temperature in degrees Celsius, specific volume in meter cube per kg. And on this side, we see that there is a very steep line, which is the saturated liquid states. And this side, we have the saturated vapor states. So this begins to look like the picture that we have been making. And yesterday we saw that on this side, all those lines where the pressure dependence is so weak that almost all states in the compressed liquid state, they all are pretty much close to this line itself. It's not falling on the same line. So that's one thing we get to know, that pressure does not have a very big effect on specific volume, and later on also, as we will see, it doesn't have a very strong effect on specific enthalpy or specific internal energy also. Okay, so this is a real behavior and what we have been looking at. And now let's see the same thing for different substances. Okay, so here is a picture. So what I've tried to do here is make a similar TV diagram for different substances. We can do that because temperature scale is absolute. It is the same temperature scale everywhere. And the specific volume is also an absolute scale. So that is meter cube per kg here. Okay, there is a small change here. I've written here temperature in degrees Celsius. This is not right. This is temperature in Kelvin. Okay, so we can make that change here. This curve at the top is for water. The bottommost curve here, this is for nitrogen. So you can see that it is going to very, very low temperatures there. Something like 126 Kelvin is the critical point, the critical temperature for nitrogen. And in between here, there are two things I have drawn. One is propane, which is this curve, and just next to that is this curve, which is for R12 CCl2F2, which is a refrigerant. And we can see the range over which these properties varies. Nitrogen goes everything below 126 Kelvin, oxygen will go below that, hydrogen will be even smaller than that. So they will all be like small domes over there. In between we get a lot of substances. Water comes here, and all of them have the same behavior, a very weak dependence on pressure on the saturated liquid side and fairly strong dependence on the saturated vapor side. But they all have the same general thing that I have been describing. So that's the important thing about this. So we made a separate plot last time where we put on the x-axis the temperature, and on the y-axis we plotted the pressure. And the lines that you see on this picture, these are lines of saturated states. So if this is the temperature, the question is what is the saturation pressure at that point? If this is the temperature, what is the saturation pressure here? And all these lines are for different substances. On the extreme left is hydrogen. So we can see that the topmost point is the critical point for each of these substances. So hydrogen goes to very high pressure, but the critical temperature is like 10 or 20 Kelvin, somewhere about that. Then you have nitrogen, which is there and goes up to about 126 Kelvin. Then you start getting here like carbon dioxide, and then a lot of curves which are very, very similar to one another. They are R22, R134A, these are hydrofluorocarbons of different types, and then this one, which is butane. The reason for bringing butane and all these substances together is that if you look at the thermodynamic properties of all these, they are somewhat comparable. And so one would say that I could have used butane as a refrigerant, or better still, substitute that hydrogen in butane or propane or ethane by chlorine or fluorine, and you start getting all these wonderful chemicals which were the refrigerants. And it was these wonderful chemicals that were responsible for ozone layer depletion. And so this refrigerant R12 I have not put here, but R22. R22 is a little bit still in use, but it is slated to be banned, and we are moving out to R134 and other refrigerants where chlorine is much less or if not there at all. So there was a huge environmental problem with these materials, and so while they are very popular for a very long time, starting about 20 years back, the global community decided that we don't want this, they are too bad for the environment, we should go for more eco-friendly refrigerants. That's what you see happening today in ACs and refrigerators. Then you have this state here, this line is for water. And to tell you that it is not just water and all these substances which behave like this, we have gone a little bit further ahead, and here these are the properties of mercury. We have seen mercury in the lab, which is a liquid. What it means is that at that 1 bar pressure, mercury has a saturation pressure, there is a vapor pressure at that point, and some mercury vapor would be getting into the atmosphere, but this is very, very small. But you can see that here now the temperatures have gone very high before we can even start thinking of mercury becoming a saturated liquid. So for instance, at 100 kilopascal, which is here, the saturation temperature of mercury is about 600 something Kelvin. It's fairly high temperature before mercury will begin to boil. And on the right is sodium. And here you can see that at 100 kPa, sodium will melt at about something like 1150 Kelvin. Fairly high temperature when it melts, and after that it can boil and change phase at constant pressure. But the pressure is increased, it does the same thing. So all these substances are basically showing us the same thing, that you increase the pressure, the saturation temperature increases, or vice versa, and this behavior ends at the critical point for all substances. So we'll now look at a few more charts to tell you that this is not just the case with materials like these. And one would ask, why are you bothered about sodium? Because that sodium is the main material which is used as the coolant in fast breeder reactors or breeder reactors in the nuclear industry. So the first reactors that are being built, the core of the nuclear reactor is surrounded by liquid sodium, or maybe liquid sodium plus liquid potassium, and we need to know the thermodynamic properties and the transport properties of those materials in order to work with them. We'll look at one more set of materials and see how their properties are, and then we'll move forward. So here's the picture. Okay, here's the plot. It may not look very clear, print is not very good, but what it has is that on the x-axis is temperature here in degrees Celsius, going from 0 degrees to 2800 degrees Celsius. Fairly high temperatures. And on the y-axis is pressure, but now the units of this pressure are very different. What you see here is pressure in millimeters of mercury absolute. So we know 760 millimeters of mercury is 100 kPa, 1 bar. So that will be something like, this is 100. So this is that dashed line here is likely to be at atmospheric pressure. So you're looking at pressures which go below that. 1 millimeter of mercury. This is one thousandth of a millimeter, 1 micrometer of mercury, 1 nanometer of mercury, and even smaller than that. So you're looking at very low pressures, which means that you're looking at very high degrees of vacuum. And that is where you are seeing all these materials being plotted here. Nitrogen, oxygen, carbon dioxide, and water are at this extreme end, followed by mercury. We just looked at that. And then we have a whole bunch of lines with similar shapes, with different magnitudes though, starting with cadmium, zinc, magnesium, calcium, lead, aluminium, copper, gold, iron, titanium, platinum, magnesium, tungsten, tantalum, chromium. So practically every material that we use in engineering is on this chart, and it all behaves in exactly the same way. The big difference is that for these metals, we get saturated states at very low pressures and very high pressures. But the behavior is the same. And so one can ask, why do I need to look at the vapor pressure curve of, say, in this case, a tungsten, W? Recall that earlier we had incandescent bulbs, and the bulb in the olden times, the bulb was evacuated because of vacuum. So tungsten was heated to a high temperature, something like 2500, 3000 Kelvin. And if you saw that the bulb goes fused, it is because that solid tungsten at that temperature kept evaporating, went into the vapor phase, the diameter of the wire kept going down, it got more hot, and at some point the bulb goes fused. That's what we say the filament breaks. So there are many such cases and many manufacturing processes where we deal with plasmas. For example, plasma deposition on a material, we get very different and very desirable properties. Where we deal with materials like chromium and nickel and molybdenum and all that, we are looking at very high temperatures and would like to work with very low pressures, create a plasma, and you do plasma processing of materials, which is a very key technology today in the type of new materials and new processes that we are seeing around us these days. So that's where these properties become important. But bringing it into thermodynamics is that they all behave exactly the same way like what we have learned about, say, water, what we started with, or butanes and pentanes and all of that. So that was the vapor pressure curve that we had looked at last time.